everybody, and greetings from Valencia in Spain, where I'm on holiday, the wonders of the internet. And welcome to the 4th Internet Reunion Club / Internet2 webinar event. My thanks especially to Internet2 and especially to Kelly Farrell, who's organizing us today. In October 2020, you may remember, we kicked off this series of webinars with a celebration of the 35th anniversary of the decision to implement the interim NSFNET backbone. Then in September 2021, we discussed the evolution of the NSFNET into the global internet. In June 2020, the event focused on using the internet before the era of the World Wide Web. And this, the 4th such event, focuses on the evolution of the routers, or as I say, being from Ireland, routers for NSFNET, the routers for NSFNET, and on the challenges involved in scaling the technology to cope with the ever-increasing bandwidth required from 56 kb in 1985 to multiple gigabits in 1995. Our speakers are Scott Bradner, Sue Hares, and Craig Partridge. They were all core participants during this period, and this is part of their story. Now, you've all seen the speaker biographies and the notes on the talks. So without any further delay, let me invite Scott Bradner to make his presentation. Scott, over to you.
Good afternoon, at least it's afternoon here. As soon as we get the slides up, I'll start talking. Here we go. Okay, I'm going to talk about early routers, the ones that were pre-NSFNET, pre-ARPANET, and the like, up through some of the NSFNET. Next slide, please. So first question, obviously, is what is a router? I'm going to differentiate it from a switch, in that a switch makes forwarding decisions between network segments using layer 2 or link layer addresses. Router, on the other hand, uses internet addresses, layer 3 addresses, internet protocol addresses, IP addresses, for example. Routers were often referred to as gateways before the term router became all that popular. The visual on the left is Evinemus 7-layer model +2. Next slide. So where did the concept of routers come from? Well, here's a candidate. Paul Barron, in his 1962 paper on distributed communications networks, which he updated in 1964 from 1 paper to 11, assumed that they were going to have some kind of switching nodes, and you can see the dots in the mesh on the visual of the network on the left. Those dots are switching nodes, and he talked about in his 1964 paper small unmanned switching nodes. Now, what he meant by small unmanned switching nodes were 6-foot racks. Next slide. And that's how it came to be. Larry Roberts' first architectural concept for the ARPANET was a star network with a big router in the middle of the country with links directly off to the hosts. And Wes Clark didn't think that this was such a great idea. It didn't scale very well. And also the owners of the hosts really didn't want their expensive big computers to be spending a lot of time figuring out how to get messages to other hosts. So Wes suggested offloading the forwarding decision processes to external devices and then interconnecting them, very much like Barron had shown in his diagram. No particular evidence that I've seen that Wes knew about Barron's work, but it came up with the same solution. So in 1969, Bolt, Brennick, and Newman here in Cambridge got a contract to build the interface message processor, or IMP, which one could call as the first big router, the first main router, and it was a 6-foot rack built based on a Honeywell DDP 516 microprocessor or mini processor. They weren't exactly micro. Interconnected 56 kilobit lines, which were the ARPANET backbone, with a common interface off to the host. So no matter what kind of host it was, what brand name computer, it used the same common interface. Now, I have a direct personal relationship with dealing with IMPs. I was told by one of the BBN people that I rescued the ARPANET. And that was because I took a contract from BBN to make a printed circuit board that would put LEDs in place of the incandescent bulbs at the top of the screen, at the top of the IMP. BBN had been sending repair people out on a weekly basis to replace incandescent bulbs, and switching them to LEDs may last for about forever. Next slide. So the NSFNET routers, the first one was Dave Mills' fuzzball routers, which are LSI 11 based, little teeny guys, not very fast, didn't have to be because the links were at 56 kilobits. Next step up was the IBM, when IBM and Merit and MCI got together to provide the NSFNet. IBM's nodes, routing nodes, were 9 IBM PCRTs on a token ring, and Susan's going to mention that a little bit later on. And the speed of that those links were T1, 1.544 megabits per second. Then the next step up on the NSFNet was 1990, where it went to T3, 45 megabits per second. And at that point, IBM used a special IBM RS6000 microcomputer or desktop computer developed with cards that were developed by IBM Research. It's interesting to note that IBM later productized and made a commercial router based on the RS6000, but in doing so, they didn't take any of the work that had been done in research. They developed entirely new printed circuit boards for the routing function. That's just the way IBM worked. Research was doing great stuff, and this particular router was probably the fastest router in the world for a period of time. Next slide. And meanwhile, while the NSFNet was starting up, there was other routers going on. BBN had a PDP-11 based router in 1976, DARPA funded. Before this, of course, Xerox had a router for, not for IP, but for XNS in 1974. These routers are all ones which supported Internet protocol. So BBN's PDP-11 based, and then MIT's a few years later in 81, the C Gateway, also PDP-11 based. I don't think they were for DARPA funded, but nice little machine. Stanford also made a PDP-11 based one in 1991. Proteon, the company, was spun off, was created, established based using the MIT software for its router, a special box, not based on a PDP-11. Cisco was also founded in 1986, and they built their box using the Stanford software. 1987, a much higher speed router was developed at BBN. It's called BBN Butterfly. That was also DARPA funded. In 1988, the Wellfleet Corporation was founded, which also produced a very, very powerful IP router. Had a good percentage of the market until Cisco took over. Next slide. By 1997, there were many, many more vendors. This illustration here is from an article that I published in Network Computing in 1997, August 1997, which was listing the results of the performance tests that were being done at the Harvard Network Device Lab that was in business from 1988 to 1990 something, and we tested hundreds of different vendor products, routers and switches, focused on routers, but also did switches to see how fast they were. There was an awful lot of fuzz going around, people who were vendors who were producing products that really weren't all that fast. Cisco products, for example, had two different modes. One was within a card. If you're forwarding between ports on the same card, they were very, very fast, line speed. 14,000 packets a second, for example. But if you're going between cards, that was done by the processor, and that was much slower. Next slide. And there was many, many failed startups over the years. Of that list that's on that slide, there are very few of those made it to adulthood. From very small boxes to you have to strengthen the raised floor boxes. Here's the Avicii picture here is an example of one of the, you have to strengthen the raised floor boxes. It was far too heavy for this existing raised floors. got a connection to Avicii also. In 1996, Avicii went public. I had done a bunch of consulting for them and got a bunch of equity in the company. And at the point they went public, that equity was worth about $6 million, and I was going to have a very comfortable retirement. But by the time the blackout period ended 180 days later, it was a very, very small fraction of that. A little bit more than paid for a six-pack of beer, but not a whole lot more. Next slide. Okay, that's what I have to say. And I'm going to turn it over to Susan. We'll have questions at the end. I'm going to turn it over to Susan.
Thank you, Scott. And I'll start in once we see the slides. Thank you, Kelly. You'll need to put it in full slide mode. Thank you. This is about routing software from the time frame 1985 to 1994. What is routing? Why don't you go ahead to the next slide? Routing is really the way software determines how packets, that is information that you send, will go from node to node in a network. So what is the purpose? Well, let's go back to 1962. J.C.R. Lydekker said, we're going to have a galactic network, globally connected computers. We're getting close to that with some of the space technology. Robert Kahn said in 1972, each network, each portion of that galactic network will stand on its own, and it will be connected to the rest of the network by other routers, that is, those nodes which forward packets, and connected to other networks by gateways. And he differentiated between nodes inside a single network as routers and nodes which connected between networks as gateways. In the first ITF in 1986, Charles Eldridge said, we need to design an area routing algorithm that has two levels, within an area and among areas. And we need to define gateway functional requirements. So one network, today you might think of that as AT&T, and Verizon has gateway defined. Why don't you go to the next slide? So how did this change between the rest of the world? Well, the forwarding was mixed. There were some in the ARPANET and Fuzzball that were TCP/IP, but a major portion of the world at that time used connectionless network software from the ISO stack, about the same as TCP/IP, but some differences. In the routing levels, how many levels did you have? A single flat level within a network or multiple? Well, the ARPANET had one, and the Fuzzballs, which is the first instantiation of the NSFNet, had two other networks and the backbone, and other networks had one, although there was an exception in the X75, and I actually worked for one of those companies that had a PDP-11 router running the CLNX and a gateway protocol between Europe and the US called X75. But the gateway protocols run by ARPANET and Fuzzball were EGP. That's the exterior gateway protocol. And that allowed networks to talk to one another. They had backbone nodes. Let's see how big it was. In 1983, ARPANET had about 113, but with the setting out of MILNET, they had 45. Fuzzballs had 6, so you can see there's a scale difference. And ARPANET also had a GG gateway to gateway protocol, but I won't pop into that. IS was used in MapTop and network to communicate inside a network. Let's go off to the next one. So when you got to the NSFNet, they decided to take a 3-tier policy routing. Now let me break that down. 3 tiers, there's the local campus network, the regional network, and then the NSFNet, which was the backbone network. There was only 14 nodes in it. It was one logical system called an autonomous system. And the regional networks also had it, and the campuses connect. And the first thing they said is this is going to be crazy difficult to control. But policy or configuration monitored what networks could be transitioned between the two. And the first thing the people said when they announced that is, we're going to go fishing for 6 months. They won't get it working. Unfortunately, or fortunately for those of us working in NSFNET, as I was, it came up and it worked fairly well. Let's go off to the next slide. Now, what did it look like inside? There was an RT running BSD 4.3. That's an operating system that was Unix. It had PSPs, which handled the T1, and one that handled the Ethernet. And then it had a routing, a processor that just ran the routing information. And they picked up things from DECnet v4 lessons. They really didn't invent anything new. They had multi-protocol, and that again wasn't inherited from DECnet. And policy routing, well, that's only configured networks can connect to the backbone. And I was working with policy routing. Let's go off to the next slide. What did the regional software look like? Well, there's a picture of one of the box. It was a Sun system. You ran a daemon on the Unix system, and it ran various protocols. The important protocol for a gateway was that it ran EGP, but it also ran RIP, which was an inter-routing protocol. So let's go on to the next thing. What happened as far as the growth? Well, if you look at it, we started out with very few networks in 1988, 1987, and we went to 70,000 or more, and the packets grew with the same amount. So this was a good growth, and the growth actually had stress for the routing. Please go to the next. Now, the first stress that we had was between EGP, which is this gateway protocol, and we solved it by going to BGP, Border Gateway Protocol. What happened is in '84, EGP was created in RC 905, and it did a full dump of routes, which seemed reasonable for a small set. But when you get to 10,000 or 20,000, we really needed to take a delta dump on what changed. And so there was the first implementation of BGP, which simply exchange reachability. Which nodes can you reach? Which networks can you reach? And it was implemented on three things: that Sun gateway system, a Cisco router, and those RTs. Well, pretty much after the first implementation, the developers realized there were a few things that had to be tweaked, and that became BGP2 in 1990, and eventually BGP3. And eventually we came to BGP4 that is lasted till today. We had some really good interaction with the ISO work that was also spun off by DECnet that helped us create a class-based routing, classes-based internet routing, and route reflectors. I'm going to go on to the next slide and talk to you about policy routing. Policy routing was, again, controlling the whole routing by using configuration files that allowed you to determine who could send traffic. So in the first case, it was just a flat configuration file, hand edited, and that was my job. And I said, that's nuts. We're going to create a database. We're going to allow some sort of general processing. And so by 1990, we had that, and that grew into allowed us to grow to the 70,000 networks. That also allowed us to spin off toward ANSNet, which was allowing us to split the research from the commercial. We ran into a trouble that the US government said, we really don't like that we're underwriting international business. This is a research network. That's what it's being paid for. So you split the two traffic, the two pattern where these traffic could flow, and that happened under ANS. And this configuration base grew into the routing arbiter database. This later grew into an international collaboration of registries in Europe, in Asia, in various places, and tried to get some protocols to help exchange traffic. As we continue to grow post 1995, you see that across the time we continue to grow in these registries, and that's really some of the undergirding of the way we control traffic even today. And we've gone to securing it as well with BGP origin checks and various resource public key infrastructure. Why don't we go on to the next slide? So one of the key things we did here is we just started working. We stopped talking and we started working. Let me show you the people who did it. Why don't you go to the next slide? There's Jeff Honing, who wrote that Gate D. There's Yakov Rector, always lecturing from IBM Watson Center, Kirk Lougheed. And I picked up both the RADB and Gate B after 1995. That's it. We're going to go to Craig, who's going to talk to you about what happened from 95. Fabulous next step. Craig, could you take it away?
Sure, happy to. Kelly, whenever you're ready. We're making Kelly's life difficult, but anyway.
Yes, we are.
Okay, and I think you need to pin me, not Sue. But anyway, okay, so I'm going to talk about the development of high-speed backbone routers. So this is to some degree a follow-on Scott's talk, and it's also very related to what Sue was talking about. So while Sue is pointing out that the routing protocols are all changing between sort of 88 and 94 or so, when we go through 4 versions of BGP and such, we're also transforming the interior of the routers. Next slide. So what happened? Well, what happened is NSFNET comes along, and one of NSFNET's goals is to connect supercomputers centers around the country to scientists. And so we started thinking about high performance networks and so forth and so on. And at the host end, it turned out to be not that hard. So there was this wonderful, if you were there, you remember it, ACM SIGCOMM 88 had about a half dozen of the key papers that you still have students read or should have students read if you teach networking. And the talks were somewhat free form in that people routinely ran over their time limits and other sorts of things. And Dave Boggs, co-inventor of Ethernet, had given a talk beating up all the theoreticians who claimed that Ethernet could only run it at something like 1/E data rates, and said, no, you can actually drive an Ethernet at 10 megabits, which was the maximum speed at the time. And in Van Jacobson's talk later in the conference, he finished his talk and then said, oh, by the way, I have these slides that show that Dave's right, and showed us the code, running code, to make a Sun workstation, a desktop computer, drive an Ethernet at a full 10 megabits per second, one workstation. And then Dave Borman at Cray Computer, supercomputer company, took Van's ideas and put them into Cray's TCP and demonstrated a near gigabit link in 1989. Now you have to realize that only a few years before, 56 kilobits had been considered a fast speed for a TCP implementation. And now suddenly we were at full gigabits. And there was some really interesting work by Bruce Davies and Jonathan Smith on how to build high-speed adapters for the next generations of desktop machines in the early 90s. And the whole point is, there we were, we actually skipped over FDDI, which is why I have Dave Mills' quote at the top. We just jumped straight over FDDI, which was 100 megabits per second, straight to gigabit speeds, at least in terms of capability of our end systems. And we did this in only a few years. Next slide. And then there was a problem, because suddenly you have all these gigabit capable hosts at the edge, and this means you need multi-gigabit capable routers in the middle of your network, each of which is connecting up a gigabit LAN. So those regional boxes that Sue pointed you at, and also the national backbone. And so if you've got N 1 gigabit LANs, you need something that runs somewhat faster than N gigabits inside to connect all those different lines. And that was hard. Next slide. Now, I could give an entire talk about how hard this is. And indeed, by 1991, Ian Leslie, who was working in the field, said, you know, to avoid wasting our time talking about switch design, we should restrict ourselves to only discussing it in the pub. But summarizing a vast amount of literature, the only way you could make these high-speed multi-gigabit backplanes to connect all your gigabit networks was to build a highly parallel switching fabric that moved data in fixed size chunks. I'm going to skip over why variable size chunks were bad. I'm going to skip over all the sorts of nasty problems of even making small fixed size chunks work, except to say that it was hard, and that the principle of switch design by the early 90s was the devil picks your inputs. And that was from Phil Carvey, who went on to found Avicii, which had those very heavy routing boxes that Scott showed in his talk. And the problem we were faced with was, okay, we're used to these variable size big packets, IP packets. How do you build a router that's taking these variable size thingies, but in the middle wants to focus on little tiny fixed size transfer units? How do you make that all fit together to build the next generation of routers? Now, one answer is you just don't buy that problem. And that was actually what John Turner predicted in 1986. He wrote a very good paper that said, look, the future of the backbone is going to be these small fixed size units of data. We should just accept that and move that paradigm to the edge. And the edge of the middle out of the network is going to be small fixed size packets. And this was eventually dubbed asynchronous transfer mode. Or you could really dig into this problem of how do you build an internet router that somewhere, or an internet routing system that somewhere at its core had these little tiny packets. Next slide. The world picked two approaches to try. One was you split up the packets as they enter each router, squirt them through that high-speed switching fabric, and put them back together again on the far side of the router and put them out on the network. This turned out to basically be building a distributed router inside the box. That is to say, we didn't have enough bandwidth for it to cross the router twice, once to a switching control processor and then to the outbound interface. We had to go straight from the inbound interface to the outbound interface. And that meant that we had to make all the interfaces actually into mini routers that could take an IP datagram in from their network and know which switch output that datagram should go to. And we dubbed the sort of IP logic that we had to put in every interface card a forwarding engine. That's what we called it. Choice two in this, how do we adapt IP over these fixed size things, is to essentially say, well, there's an IP to small little chunks of data, which are called cells space. And at that boundary, you map your IP datagram to a long-lived flow and squirt it across a chunk of the network. And when it reaches the end of the flow, it's reassembled into an IP datagram, and your router makes a decision about which next long-lived flow to squirt it over. This works if you don't look at the full packet very often. That is, you don't put the IP datagram back together and have to do a route lookup. Then it all works. It gets you in trouble if you have to keep doing IP lookups on top of creating all the dynamic long-lived flows. So you needed a stable mapping between the IP layer and the cell flow layer. Other detail here is if the flows were too long-lived, the answer is you'd say, well, why don't I just get a leased line instead? So you had to see a certain level of dynamism at the cell layer, but not enough that you were inclined to buy yourself a high-speed SONET channel, for example. Next slide. So going back to that first approach, here's the kind of box you had. You had a control processor that went with the switching fabric. And what it did was it responded to any messages to the router. So the routing protocols would talk to the control processor. So would network management, okay? And the control processor would then load the information about the router, the big box, to each of the forwarding engines on the interface cards. And they would then know how to route the IP datagrams through that big switching fabric in the middle. Initially, we thought there would be two forwarding engines. The idea was that the receiving forwarding engine would know the network it was attached to, would do some header update and validation, and then squirt it across the outbound interface, where the outbound forwarding engine would understand things like how to do network, so IP address lookup, ARP, or whatever on the outbound link, and would understand the outbound encapsulation. In practice, it turned out we didn't need the outbound one. The inbound forwarding engine was fully capable of doing everything, but we didn't know it initially. So this was the model we were working with. Next slide. So by 1992, so notice this actually took us 4 years of hard thinking. There were several people who had realized that this forwarding engine architecture was the answer, or at least a possible answer, to building high-speed backbone routers. The group I led at BBN, I had a hand time implementation for a particular processor, which is very nice, the DEC Alpha processor, that could handle 6 million datagrams per second of routing decisions. So that meant we could go about 6 gigabits per second on average. And in worst case, if all the IP datagrams were tiny, we'd be at 2 gigabits. And that was still enough to drive future links, because we were looking at the potential a few years out to get what were called OC48C 2.4 gigabit line cards. And the answer is we could get there. Cisco had started on something called the Silicon Switch. So people were building forwarding engines. Now, one nuisance about forwarding engines is the early forwarding engines assumed there was a working set of routes. This came from work in the late 80s that showed that actually you only use a small working set of routes at any given time. And so the idea is the control processor would give you a small working set. You go very, very fast with a small working set. But that came undone. Next slide. It broke. And this is sort of Carvey's "the devil picks your inputs" ruled again. We couldn't deal with small working sets, so we couldn't use small associative caches. We actually had to copy the entire routing table that was collected by the protocols that Sue talked about, BGP and such, and download a copy into every forwarding engine. Now, that was painful because at the time, a full route lookup took O of W, where W was the width of the address in bits. And so for an IP address at the time, 32-bit address, that was 32 memory accesses, far too many. And so we had to figure out some way to deal with that. Concurrently, there were people, remember my approach 2, in which you put datagrams onto an ATM link or a cell link and squirt it across for bit to on a long-lived flow. There was a company called Ipsilon Network that was trying to do that approach. They ran into the same problem, only it expressed itself as the flows being not stable. Where the traffic wanted to go in the network was varying too fast. And so finding a way to map datagrams to stable flows turned out to be a very hard problem. And they kept having to revise their software, and people would report that the Ipsilon routers would fall over because suddenly traffic dynamics changed. Next slide. So our big problem at this point is we need a full snapshot of the routing table, which became called the forwarding table, or the FIB, that we downloaded into every forwarding engine. Ipsilon had already demonstrated that their version of the solution didn't work. We had to find one that worked. So what did we do? Well, basically, I, on behalf of the community, went out in '95, went to a bunch of universities and said, please, 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 find us a better way to represent the routing table. One that is reasonably small, that we can load into all the forwarding engines and has good lookup times. And we got 2 beautiful solutions. And there are now a large number of them out there. It became a whole cottage industry of devising such data structures. But the 2 early ones, one was from a university in Sweden called Luleå University, which was incredibly space efficient. You could smash the entire routing table into 100 kilobytes. The other one was from Washington University, St. Louis, which had a beautiful property that the lookup time was actually logarithmic in the length of the IP address, which meant that 6 memory accesses would tell you where any packet needed to go. What's more, Luleå allowed you to have different banks of memory for different lookups, which meant you could do all sorts of nifty pipelining approaches, divide the table up for easy updating, things like that. So it was a very, very nice architecture. Next slide. So here we finally had it together. We figured out how to do forwarding engines. We figured out how to deal with the routing challenges. We figured out how to wrap it around a high performance switch. Well, almost. There were still some challenges. You had to optimize the switch architecture for IP datagrams, where those fixed cells, those fixed chunks of data going through the switch, were they to be somewhat bigger, smaller? This was a bandwidth issue. If you made the wrong choice, and one router vendor who understood the forwarding engine and switch concept, called Netstar, made a bad switch choice, your router didn't fly. I remember being stunned by the Netstar router when it was suddenly on the interop show floor and going, oh my goodness, they may actually take the market from all of us, and that because they were the first, and it fell on its nose. Another surprise was SNMP. So SNMP, you had to sweep up all the SNMP counters from all the forwarding engines, a consequence of distributing the intelligence around the edge of the box. Well, that turned out to be hundreds of megabits of information per second. So we actually had to build separate buses for SNMP into our routers, which was something of a nuisance. And then there were many tricky details within the forwarding engine, designing the hardware so that it could focus on datagrams and not cache sync for forwarding tables, and didn't have to worry about SNMP very hard, all a challenge. Next slide. Still, by the end of 1996, so now it's been a full 8 years since we saw our first high-speed TCP implementations, 2 or arguably 3 teams had figured out the big and little challenges. One was a DARPA project that I led with Phil Carvey and Walter Milliken. We were paid by DARPA to do a public router demonstration, in part to put pressure on the established vendors. There was a team at Juniper Networks. Indeed, if you read the Juniper and BBN patents, they're almost the same. And it is this basic architecture we still use today. Cisco had belatedly started on its GSR 12,000, otherwise known as their big effing router. There are a couple of lessons from this that were important. One was, form doesn't have to follow function, right? So John Turner's argument from 86 was, the inside of the network somewhere is going to have these switches moving small chunks of data in parallel. And he argued that meant you made small chunks of data the dominant paradigm to the edge of the network. What this work showed with tremendous effort was that you could actually put a wrapper of variable size packets around these fixed size backplanes. The other thing was how complicated routers were. And one of the things that was going on at this time was they kept getting more complicated. SNMP barely existed in 88. We did not have BGP. Traffic patterns were changing. Scott Bradner also started developing tests requiring us to have certain capabilities in our boxes. So we were concurrently with dealing with this tremendous performance problem, having to deal with the fact that the sort of metrics for success were shifting on us over those years. So it was a very, very interesting time and very dynamic and rather scary, in fact. So with that, I believe I'm done. Next slide. Yes. So I also want to shout out to 2 people who were also in this area at the time who read my slides and corrected some of my errors. Any remaining ones are mine. So I think we're now open for questions. Thank you.
Thank you, everybody. That's fantastic. The 3 presentations and done at top speed. So we have plenty of time for questions if there are questions. Scott, you've answered the latest question. Can I turn to you? Why did IP routing win over all the many alternatives? From Brian James. Scott.
Well, I think it was the environment that made that the case. IP survived, and I've got a book that's being published hopefully sometime this year by Oxford University Press, which addresses this actually. It's called Forks, the major decisions that got us the internet of today. You were critical in one of those decisions. You, Dennis, required that the devices on the NSFNET only could communicate using IP. Could not use DECnet, even though there were DEC computers connected to the network. They had to be IP. The ARPANET was IP. DARPA paid Berkeley to put TCP/IP stack in their unit version of Unix, and then that was distributed at very low cost. So anybody making a high performance workstation would want to use Unix that would get the Berkeley version, would have TCP/IP stack in it. So the IP was supported widely, wasn't supported on PCs, and some third parties made a bundle of like Wollongong selling PC IP software, but Apple supported IP on Macs very early on. So it was available. The other thing was the alternatives were just too confusing. There were too many of them. It was AppleTalk and DECnet and IPX and something to do with various local vendor products, and it was not very easy to deal with. Although many of the earlier routers were multi-protocol routers, Proteon and Cisco and Wellfleet were all multi-protocol routers, but as you had to move to IP in order to communicate across the NSFNet and the regional networks, which grew into more of the internet service providers, that's the natural progression. All of the others tended to fade away in the enterprise. And once it was gone in the enterprise, IP was what was left.
So I have another view, if I may, for just a moment, two other things. One is, and this was in part NSF driven, but there was a general principle in the late 80s that if you built a solution that wasn't designed to be global from the start, it was never going to be global. It was very hard to stop relying on the timing of Ethernets and things like that. And so the internet, by growing globally and being pushed by NSF and DARPA in the late 80s to grow globally, suddenly developed this, first of all, it was designed to be a global network. And second, in the late 80s, just in time, we figured out how to do it. And you heard Sue talk about the realization of, oh, we need a policy database. There was lots of learning going on, but we had a substructure designed to be global, and we were the guys who led in terms of figuring out how to actually make that work. And the only competition in that area of global networks was DECnet. And DECnet stalled trying to make a transition to OSI, and that left a lot of room for the internet community to just take over the landscape. The other thing was email. And this goes back to Scott's point, because most universities were running BSD Unix or something like that, and they connected initially to CSNet, which connected them to the ARPANET internet email world, but it didn't give them actually internet connectivity. But that meant that they were using software that used email addresses that were ARPANET compatible or internet compatible. So when NSFNet showed up and said, hey, we'd like to connect you to the internet, everyone said, oh, that's great, because then I don't have to change my email addresses at my campus. And so there was a real administrative instinct to go take the technology that doesn't require me to change my email addresses to something else and connect up. And that was made very, very easy. And that was because the email community had standardized on email addresses in the early 80s, and particularly RSC 733, not even 822 addresses. And then we standardized on domain names in early 1986 across UUNet, BitNet, CSNet, and all the other academic networks.
And that actually helped get a lot of our early 87 to 94 networks working. If someone couldn't get email, we assumed we had to go work on fixing the network. So there, one other little gem there is that the support by IBM and MCI in the early days was critical. If something broke in the middle of the night, it wasn't just the professor getting out of bed and going in and checking on something. The actual NSF nodes were hosted by a real squad of IBM FEs who ran out there and fixed the thing. And the MCI had 7/24/365 service. So when we started that really gave us a big push of reliability that was not expected. Again, going back to they're going fishing. The same thing launched into some of the international connections in the early days, because they became the way to get email across the internet, and for the researchers at the supercomputer sites, that was critical. Their grants were based on that type of speed. And if they didn't make that speed, they were on your case. I remember some of our first reviews from NSFNet where I had a researcher say, how come I can't get that gigabit speed through the NSFNet? So the expectations change due to email and due to these national science supercomputer centers.
Thank you, Sue. If anybody out there has a question, please use the Q&A to type it in. We have a few minutes to address questions if you have them. Now, panelists, do you have questions of each other? Or even minor disputes that you want to raise at this point? I doubt it, but nevertheless. Scott? No?
I've dealt with both of these other folks exhaustively over the years, sometimes to their benefit, and more often to mine.
Craig?
Having consulted for both of them, actually.
Yeah, no, I've known, God help me, I shouldn't even confess to how long I've known Scott. I don't think I think I first met Scott when I was undergraduate. God help me.
I think that's correct.
No, I think I don't think there's any disputes in between us about what we've said. It all fits together. I think the only thing I'll say is I think Scott's underplaying how important his testing of routers was in the early 90s in terms of shaping some aspects of the router market. I mean,
it wasn't just performance testing, it was function testing as well. And
that's right.
Just to see what SNMP they supported and things like that. So what routing protocols. So it did quite a bit.
Oh yeah, no, they were massive reports. And I remember they were eagerly awaited every 6 months or so, but they placed a lot of, they both professionalized and placed a lot of constraints on router architectures. I mean, it's worth remembering NSF in like 88 did the first router requirements. And it was a few pages long, and you could build a wide range of things and claim it conformed. And that really didn't work in the production space that NSFNet became, and Scott became sort of the arbiter of a lot of that. And I don't think it was until the late 90s that the router vendors fully got together, I think under Fred Baker, and put together a new router requirements that actually made sense. And then, of course, it was a book-length document. It was a massive RFC.
But even then, it didn't have some of the how-to and the definitions. As you worked on router software, the type of careful, this function is there, this function is not there, we're still benefiting from today, because in the ITF, in the BGP world, we're still requiring you must give us the same type of information that Scott gave us, where you gave us, here's the function in the document that you said you're going to do, and here's where you've actually tested it. That still is the undergirding of some of the 99% up functionality we have today. That type of test is critical, and where the vendors pull away from it, you find that they suddenly have errors that are long-lived. And where do you see that? You see that when the cycles for releases become longer. It's because they didn't pay attention to the things that Craig did, the attention that Scott did, where you check each one of these functions carefully.
Now, note that the testing I did was reflected in the IETF benchmarking methodology working group, which I co-founded in 1990. It's still going on, and it's producing RFCs regularly of testing advanced protocols, whether it's or performance of firewalls, things like that. And to Sue's point, there's a lot of detail that you need to specify. And those RFCs over the years have done a lot of specification of how to look at performance issues, but implementation issues in protocols. And it's been quite rewarding. I will say it had an awful lot of fun at Interop, Network Plus Interop, because I'd have a room with 600 or 700 or even 1,000 people in it, waiting on my jokes about router vendors.
Yeah.
I'm going to ask a question, if I may.
We got a bunch of questions popped up too, by the
Yep.
way.
Oh, there, I don't see them. Can we just?
Well, here, let me try a couple. So,
Oh, yeah, please.
so let's see. Laura asks, what decisions did Cisco made that lifted it to the top of the heap? And I will argue that, in fact, Cisco very narrowly missed fumbling in the mid-90s. So the answer is, in the late 80s, they had a beautiful vision, which was that a router was essentially some really good software, the Stanford software, much improved on a multi-bus backbone with a 68,000 processor. And they could build it in any configuration that you wanted. And they would build a line card for any network you thought you wanted to attach to it. The IP over everything ethos at Cisco was great. And so they developed this huge customer base of people who had learned how to manage their routers and run it on their networks. And then Cisco completely dropped the ball for a few years on building the big backbone router, to the level that actually there were articles in the press condemning them for not investing sufficiently. They did not invest in switch technology. They didn't have a skunk works. They ended up having to buy switching companies to figure out how to build their backplanes. And the answer is they just barely, by the skin of their teeth, because they had a large enough marketplace before that, managed to take hold again when the BFR came out and, stay the leader in the mid-90s. But it was a close call. And I see I provoked a bunch of people, including Scott and Sergio, and says, oh, fun, go.
Scott, you want to come in on this?
I would add to that Cisco's competition self-immolated. Wellfleet brought out a product which you could not use a command line on. You had to use a GUI interface, and the geeks don't want to use GUI interfaces. So to use a command line, you typed ASN.1 commands to the router. You pretended to be an SNMP management station. And Proteon from the beginning had a command line that was imparsable by humans. And so those two vendors just collapsed on their own. Wellfleet had to back down and put in a Cisco-like command line language later on, but had lost a huge chunk of the margins. They were much bigger than Cisco for a while, and then they just collapsed when they did that, when they modified their command line. And the other vendors never achieved escape velocity. Things like Avicii spent too much time and effort on the niche case that wasn't reached, that of performance that wasn't needed yet.
That's the real key, is the success ratio had to do with right sizing the performance to what was needed at the time. And sometimes just selling. I got to tell you that Cisco's original selling atmosphere, the first VP of sales, they said, would sell his mother down the river. They sold. So by having that first advantage in that amount of background, you had the first advantage. By the way, I also entered in the chat that I was a part of the company that had X25 and X75 in the 80s, but didn't make the transition into the internet. So there were lots of companies that made choices that were regrettable, but didn't quite make it.
One relative to X25, it's not generally well known, but the folks that developed TCP/IP, VidSurf, and the network working group, and offered TCP/IP to ISO as the future generation internet protocol, network data networking protocol. They were turned down, with one of the arguments being that the telephone world had X25 and therefore it had everything they needed, plus the fact that X25 was a telephone world protocol and therefore the telephone company was in charge. The problem with TCP/IP was it bypassed the phone company. All they had to do was move bits. So they weren't in the value proposition.
Right.
And so one of the U.S. delegate to ISO was one of the most vehement objectors to the idea that they should take on TCP/IP.
So two things that persisted into the early 90s, and the telephone industry adopted ATM because they thought they could push the internet technology aside, and because the telephone community actually had experience in building those high-speed switches already for the voice network. And they were very candid that they didn't want to buy into TCP/IP because it made them wire pullers. Now, this also gives me a chance to tell my favorite Dennis Jennings story, which is an X25 story. So I'm going to tell it briefly just because we're here and we're having fun with history. So there used to be meetings annually of all of the people running TCP/IP academic networks around the world. They were informally known as the Landweber workshops because Larry Landweber had originally convened them. And Dennis hosted the one in, I think, 87 or 88 in Dublin. And he put us up in a nice resort hotel outside Dublin. And it was a wonderful conference in many dimensions, and a lot of important discussions about improving international connectivity happened. But to deal with the fact that we all had an email habit, Dennis had managed to run an X25 link to the hotel from University College Dublin, and had actually had it billed to his own personal academic account. And he told us to try to be reasonably nice about bandwidth. Well, unfortunately, there were a couple of rapscallions more than a couple of rapscallions at this event. One of them was Dave Farber. Another was Robert Eltz from Australia. And at one point, Robert mentioned this wonderful software that he developed to do some networking thing. And Dave, who was an incessant pack rabbit who loved to have new networking software, said, "Oh, can I have that?" And Robert said, "Sure, there's an X25 connection here. I can connect to the Australian X25 network and download it for you." And they're in the midst of downloading this multi-megabyte image file when Dennis walks in to discover that his account has been hijacked to make an X25 international call to Australia. And he had no control over it. And he was sort of like, "What are you doing to my bill?" So anyway, just a fun memory.
You're muted, Dennis.
Thank you for that. Yes, I do remember. The question I get asked, apart from being blamed for every internet thing that happens among my friends and associates, the question I always get asked is, did you think it would go global? And to which my answer is, well, we had huge ambitions for the NSFNet. We were going to connect every researcher in every research university in the United States together to be able to access all resources. We were hugely ambitious, but no, we never thought it would become the global infrastructure for every communications. And that for me is a wonder. It really is. Craig.
So I remember when I realized that it was going to win and be the global infrastructure. And it was a very quick realization over the course of 1988. And it was just sort of like, oh, and you can see this in some data. So for example, you can see it by the number of people at Interop, which I believe in late 87 was 300. And at the end of 88 or first Interop of 89 was 5,000. And there were show floors, and suddenly there were mobs of people on show floors. And you could just, in 88 was pretty much you could just suddenly see the internet take off, because in 88, we solved the congestion control problem well enough. We were close to solving, we were getting BGP to stagger along, and we were moving towards the BGP solution. We had SNMP, we had network management working. All the pieces started to fall into place. And when you looked over at what was available in the OSI standards, which was the supposed other choice, they didn't have them. Now, DECnet had them, but DECnet had announced they were moving to OSI with great effort. And so the problem was there was a whole gap in technology required to build the global infrastructure that the internet community had finally managed to bring into place, because we had finally reached the deployment points that we learned enough to do that.
The OSI paper stack was vast, feet of paper in order to show things. Their code base, it took 6 times the code to implement the OSI stack that it did for the equivalent amount of TCP stack at one point. But anyway, we have reached the end of our time period.
I won't be quite as negative on some of the OSI. The CLNS stuff was fairly reasonable, but the connection-oriented stuff was quite complex. Having done both.
Yep.
Sue, thank you very much indeed. We've run out of time. I only add to close this, and thank you everybody for attending, and thank you especially to our speakers, Scott, Sue, and Craig. Thank you for wonderful talks. But I realized that this was going global, at which point I added to all my emails, I told you this internet thing would catch on. Take care. Good night. Thank you very much.